Hey, Siobhan. Can you see me okay? Just holler if you're in. All right, if you all are here, feel free to check in on Slack. I guess I need to email one more email out because the first link went bonk. I just pasted a new one in Slack, so don't use the one in the email yet. I'll reply all. That link went bonk. Try here. Hey, Siobhan. Hello again. So far, it's you and me, man. I'm gonna go get a caffeinated beverage. I'll be right back. So we'll get started in 7 minutes or so. Okay, guys, be right back. Hi, Katie. Got what? Da, da. I'm echoing. Hello, hello, hello. Am I echoing on other people's stuff as well? People tell me if I'm echoing on other people's stuff as well. Hi, Dama. If it's on my end, that's bad. If it's on your end, I mean, it's also bad, but it's bad for you. And and we can, the way to sort that out will be something else. I'm not echoing on Dalma's. So Charisse, my guess would be that it's maybe you have speakers on, or maybe you have two windows. I bet that's what it is. Totally. You have me open in one window, and you also have me open in another window, and there's a lag. And so you're hearing me say this, say this, say this, say this, say this, say this. Personal problem. As personal problems go, it's pretty easy to solve. Hi, Becca. I'll assume that not echoing for me is how you say hello. Hi, Anisha. You do have two windows. Awesome. I get like tech support extra points, huh? Because I didn't even get to see your computer. Just like, it's like a mind reader, right? I can tell by the vibrations in the ether that you have two windows open. No, it's fine. That's fine. Let's see who else is here. I'm on the TV. Cool. Hi, Ray. You guys in a big room, or are you just Chromecasting me to? That's a neat idea. You could totally Chromecast this to your big screen. You sit back in a recliner with popcorn. Take notes very assiduously while eating popcorn and watch me on the big screen in your leather recliner. Oh, this is totally unrelated, but it occurred to me that you guys might not know about this, but you might like to know about this. Have you guys ever heard of a thing called Autohotkey? Hey, Giovanni, you are back. Welcome back. You're in the right class now. Vibrations in the ether. That's right. Yeah, I'm just a meme generator. All right. So this thing, I have a little file here, which I don't know if you guys can see. This is my shortcut. But I have a program called Autohotkey, which you can see down here. And it runs scripts. What it does is it just sends stuff to your keyboard. So this is what it looks like. It's just a notepad file that sends a bunch of stuff. And it looks like programming. Hi, Azalea, welcome. But it's really pretty easy to learn. Send just means send to my keyboard. And so, for example, when I find myself saying something a lot, I created an Autohotkey script to do this. So here, let me run Notepad so you can see how it works. But so, for example, I have to sign a lot of emails. Hi, Eli. So if I want to say thanks, Dr. D, I made it so I can. So this is like what you can do on your phone, right? So or TY, thanks, Jason, if I'm talking to somebody who's not a student. Or if, let's say, for example, let's say some of you didn't turn stuff in on a separate page at the beginning of the semester. So I made this thing so that it would automatically fill an email out to you, right? So all I have to do is type separate page, and it goes, hi, for future problem sets, please complete your work on separate pages. Thanks, Dr. D. So some of you received that, right? And if you make the terrible, terrible mistake of cheating in my class, I have something special there. I also have one called full sig. I don't know if it works, it doesn't really work in Word exactly. But it does work in my email. So for example, I generally use, here, I'll show you guys my like very, very clouded inbox, a very, very cluttered inbox. But if I want to compose an email to somebody and I want to say, hey, person, good ideas, brilliant. And then I want to say, TY, thanks, Dr. D, and full sig, boom, and it just puts a full signature in there, automatically formats that. It's super awesome. I highly recommend it. Autohotkey. And it's one of those things where like the first time I made it, I just made like the simplest stuff. So you can see I started by just saying, thanks for letting me know, right? So if I go into if I go in here and just type TFL, just says, thanks for letting me know. So that's for like, if somebody would tell me they can't make it to class, I don't want to just not say something, but like on some level, like you can't make it to class, that's sad, but I'll see you next time. So I just want to send something back. So thanks for letting me know is where I started. Oh, I wonder if I have. It's the one I showed I made one for my daughter because she thought it was cool. Let's see if I can find that on here. The members of this group are. Sorry for the delayed response. I hope that helps. I don't remember. In any case, oh, there it is, VZA. So my daughter was like wanting to know what I was doing one day, so showed her how I could just type Violet is the awesomest. It was really cool that I made my computer do cool stuff. So it's called Autohotkey. I highly recommend it. If you ever end up in a job where you have to send a lot of the same emails and you don't want to screw anything up, it's a really good way to like send scripts to your keyboard so you can automatically send like snippets. It's kind of like a super powered clipboard, but it turns out there's also other stuff you can do with it. What's the cheating one? Oh, what does it say? You want to see what it says? It is called Acad Boom. It says your most recent problem set submission contained material lifted from the solutions. This represents a serious breach of academic integrity. In the future, in an email, it's got line break, so I can show you. If I type Acad boom, and it just says, it automatically says failure to follow these guidelines in the future will result in an academic integrity violation report submitted to the Academic Integrity Office. The goal is to scare people like within an inch of their life, and then if they do it again, then we have to go through the whole rigmarole. But a few semesters ago, I had somebody who copied and pasted and out of my solutions guide, my solutions to a problem, and sent me my own answers, which is really not okay. Like, I'm going to notice. Oh, you lost sound, Ray. I'm sorry to hear that. Maybe reload it. You're not allowed to send me my own answers. Also, I will totally notice because I wrote them. And so when you copy and paste my solutions, I notice and it makes me angry. And the problem is, like, it makes me angry enough that it's hard to reply. And so this way, I don't have to think about it. I just say, hey, cheater, pumpkin eater, Acad integ. And then I just send it. I don't have to think about it again. I can go do something else. So makes me feel better about things. I stew less, so that's useful. Anyway, I have a lot of emails now that I send. Oh, the other cool thing, this is totally unrelated, or not totally unrelated, somewhat related to how people who are good with Excel and stuff do their job better. So I mentioned in class a few times that I'm the corporate sponsorship. I know, right? It's crazy, right, Becca? Cheater salad. That's much. I don't know if it's healthier than. Maybe you could put pumpkin seeds on your salad. But I'm the corporate sponsor liaison, SBA representative, point of contact. And so I want to be able to keep track of all the events. So what I did was I made myself a spreadsheet that has all the events that are going to be going on all semester. It has the date, the event, the sponsor, the goal, and then stuff that I have to do. And why did I do this in Excel? Well, the reason I did it in Excel, hey, Brandon, the reason I did it in Excel is because it allowed me to do stuff like this. So here I have the date. And this looks stuff up from, well, I guess this one doesn't, but this is when I'm planning on releasing information. These are the blurbs, so I can look up Resumania, I can look up employer and residence. And then this is a blurb where you see it just says, space will participate in Resumania, space will be an employer, space need to write blurb. And then if I type in today's date, hey, Ajwa, if I type in today's date, this table looks up a bunch of stuff and then and adds days. And then tells me what's the stuff that I need to do. And it also creates an email blurb. And then this thing here is awesome because what I can do now is I can just copy and paste this. It automatically generates an email for me. So if I copy and paste this into, let's create a new notepad. It automatically generates this email for me, which is really nice because I'm terrible at keeping track of details. Hey, Adriana. I'm terrible at keeping track of details, but I'm great at writing a spreadsheet, and spreadsheets are awesome at taking care of details. And so every week I have to send out this email. And so it took me like 2 hours in Excel to create this automatic like thing that just it'll look up in the future what events are going to be happening. And then it just creates creates an email. Obviously I have to go in and clean this up a little bit, but it's really powerful. And so Excel is really useful. One of the ways you can use it is to create like a regular, if you want to automate an email process. I'm sure there's software out there you can pay for that does it. But if you're good with Excel, hey, Luisa, if you're good with Excel, it takes like a couple hours the first time you have to do something like this. And now, next semester, when I'm doing this again, all I have to do is load in all the events here in the events tab with their dates, and it will automatically create the emails for me, right? And, as long as I change this date. to the correct date to today, it automatically creates next week's emails for me. So I don't know. I just thought I'd show you guys just to spark your imagination. It's totally worth it to get good in Excel, because getting good in Excel makes you better at everything. I've done a ton of stuff in Excel. Maybe one other piece of inspirational stuff. I haven't been using this lately because our schedule has changed and I haven't fixed it. But to show you what I design, one other thing I designed in Excel. This is a menu generator. So you can see the last time I used it was December. I haven't used it since December, mostly because our semester's changed. Hey, Giovanni, thanks for the heads up. Oh, is this is just yeah, it's all on one page. So the way this works is I just type in what month it is. So let's say I want for April. April's coming up. I change this to month 4, and it automatically changes the calendar to April 2015. It's got a March and a May, and I can copy and paste this into a Word. And to show you what the finished product looks like, it looks like this when I'm done. Right. So I create this calendar, which I can then print out. And I format it a little bit and add some special stuff. But the way that it works is I was noticing that I was spending like a lot of time like trying to come up with menus for the month. And so instead I thought, you know what? Why don't I just let a random number generator do that for me? And again, this probably took me like 2 hours one day. And what I have is sort of you can see I have a Monday lookup table. Okay, welcome back, Ray. I have a meat lookup table. I have a Friday code, which tells me whether it's pizza night, I think. Vegetable lookup table, weekday lookup table, pork, Friday lookup table. So I have a bunch of like lookup stuff here, but it uses just a random number generator. It's not as it looks complicated. It's not that complicated. And what it does is it just generates a bunch of food so that I don't have to decide. The cool thing is that whatever we had on Tuesday, so if Tuesday is a chicken day, then you can see we had chicken salad sandwiches and chicken tacos. If hey Abu, if we had ham on one Tuesday, then it makes ham sandwiches and ham soup. If we have meatballs on one Tuesday, meatball sandwiches and burgers. So there's like a meat for each week, so you can just buy enough meat at the beginning of the week. How did I take the fun out of lunch? Are you kidding me? I made lunch awesome. Because lunch no longer became something that I had to like argue with my wife about. Now I just print one of these each month, and it's like, yes, I don't have to worry about this anymore. But yeah, I don't know. This is something that I bet you didn't think you would use Excel for. I think one of the reasons that stuff like this occurs to me to use Excel for is I first used Excel when I was around 11 or 12 to make a map of the neighborhood where I delivered newspapers. Hey, Barone. So I didn't know that like the purpose of Excel wasn't just to like take it and do this with it, where you make like a grid and then like, oh, this is a street. So let's get rid of the vertical borders in here. Like this is what I first used Excel for, was like, okay, well now I want to make a street, and then these people get newspapers, and these people this person has a box. And so that was how I first used Excel. I didn't even know it was for like math and stuff. I was just like, cool, I can make a map of the neighborhood where I deliver newspapers, and then I won't forget who's doing what. And so since that was how I got started, I kind of just figured I could use Excel for whatever I want. And so if I want to make a calendar, I use Excel. If I want to make an email generator, I use Excel. I use Excel for a lot of stuff. Anyway, just kind of a tickler for ideas of incentive to get good at this stuff. Because if you get good at this stuff, you never have to decide what you want to eat again. You can always, there's always a rough draft, right? So we print this out and then you get to decide, do I actually want chicken salad sandwiches or do I want it to be taco night tonight? So Excel is a powerful tool. Hopefully you guys are inspired to go solve the world's problems, or at least solve your problems. Little did he know, ruin it. Are you kidding me? When I made it, my wife was like thrilled. She didn't. So when my wife married me, I was like an out of work English major. She had no idea like I would also eventually become a PhD economist who knows how to use Excel and stuff. So all this stuff is bonus. Little did you know, it would run his life. Yeah, that's all right. I'm okay with Excel running my life. It's smarter than I am. All right. I extended the deadline for problem set 8 by 2 days because we're only learning some of it today. So I wanted to give you guys a couple days to do that. Part 2 analysis. I reached out to a few of you who I haven't even heard who in your group is doing what. That is bad. Like, come on, people. You got to bring it a little bit. I want you to be posting stuff, your spreadsheet, the work that you've done so far in your Slack group channel. So put it there because that's where I'll take a look. I see Jason's typing. Welcome, Jason Leaks. Yay. Hey, Jason. Good to see you. Anything else? No, I think that's good. Exam 2, obviously, on Tuesday. Building openness allowing. If I find out that building is going to be closed, obviously we'll change plans. But from what I've heard, it is closed till Sunday for repairs and will open again on Monday. So that is the current plan. What else have you guys been up to before we move on, head on with the class, besides just making cool internet stuff or making cool stuff online? I got into a Twitter argument about Superman earlier and also went rock climbing yesterday. So that's what's going on with me. People being wrong on the internet is hard. Hopefully you guys are winning all of your arguments. Got a few people typing. I'll wait till see what they have to say before we move on. At least I can get set up to start where we're going to start. Where's my pen? Just finished a Cootie finance test. Oh, those are legendary. How'd that go? Louisa got into an. Are you okay? My goodness. I don't mean your car is sad, but ouch. Are you? Hopefully you're okay. You didn't. You're on. Your hands work, right? You're typing. Hopefully. That's terrible, Louisa. Sorry to hear that. Am I seeing BVS? Oh, Batman versus Superman. I will see it. I haven't yet. I don't understand. The argument I was getting into was like, I'm a Superman fan. I'll out myself there. My brother was a Batman fan, and I always liked Superman. But the Superman that Hollywood keeps making is the Superman who punches stuff a lot. And I never thought of Superman that interesting as a guy who punches stuff a lot. Rode dirt bikes through a neighborhood that isn't yours. Okay, hopefully you didn't get arrested or chased. Coke and then coffee. Like I don't. This has water in it. There's water. It's mostly water, right? That's like the first ingredient in each of these things. Coffee is good for you, by the way. But the most studies seem to show that it is better for you than other things. Went and saw your mentor. But back to Superman. Superman's like actually there are a bunch of different versions of Superman. And the most interesting version of Superman, yeah, Ray wins, that's right. The most interesting version of Superman to me is the guy who's trying to figure out like, hey, I can pretend I fit in with the mainstream like a normal person, but also secretly like I'm actually this gigantic weirdo. Like how do I make this, and also I'm an immigrant who came from somewhere else, but then I'm adopted into this other family. Like, how do I take these two identities and how do I be true to my heritage, but also be true to the society I live in? How do I take the skills that I have and make them useful and not destructive? That's super interesting to me. They're like, hey, I can punch something super far. Clooney Batman, best Batman. No way, Keaton Batman, best Batman, but one man's opinion. Or animated series Batman, best Batman, right? From now I'm just aging myself. Yeah, but in any case, I think they could be telling good Superman stories by like not having him punch the universe. But for some reason, they just want him to punch the universe, and it just seems boring. No wonder people are bored by it. It is boring. He's more interesting as a human, as somebody grappling with humanity. Clooney was good. Clooney makes a good Bruce Wayne, just doesn't make a good Batman. All right, this has been way too long talking about nonsense. But anyway, I'll probably see it. Yeah, that's right, Jason. Yeah, I showed that to my daughter. She liked it. So she's 8. It holds up. All right, so I wanted to start with a practice problem doing the stuff we did last class. So we're going to start with one that you didn't have to do so that you'll have some practice. And we're going to do but that's why it's boring to be like that. That's right. Civil War movie, that'll be good. I was always a DC guy though. I was always like a Green Lantern Flash fan. So what we're going to start with is problem 618 here, talking about stock companies. So you guys have this good. I think I handed them out, so you should have them. The average stock price for companies making up the S&P 500 is $30. No more distracting me with Superman, Batman stuff. The standard deviation is 820. Assume the stock prices are normally distributed. So if we want to try to solve this kind of a problem, we're going to just go through the 4 steps. We learned them last class. So we're going to pick up where we left off. Step 1 is to take the problem and turn it into a picture. There's a normal distribution. It says here the mean is $30. The standard deviation is 820. And then the first part is, what is the probability a company will have a stock price of at least $40? Okay, so we got $40 here. And then the probability that it'll have at least a stock price. Remember, probability is area. So we want to know this area here. This is going to be our P. That's our area. We don't know what it is. But that's step 1 done. Step 2 is to relate it to the standard normal distribution, because while this is obviously a normal distribution, we don't have a table that tells us anything about this distribution. So we're instead going to compare it to our benchmark distribution, the standard normal. And I apologize in advance for my drawing skills on a tablet. I'm not actually using a tablet, by the way, or I'm not using a tablet PC. I'm using a Wacom tablet. Why is 40 above 50? 40 is not above 50. 40 is above 30. Good question. Because I have bad handwriting. And so 0 is the mean of the z distribution. 1 is the standard deviation of the z distribution. And now I have two sigmas up here, so I'm going to subscript these just so we're clear which one we're talking about. Sigma x is 820. Sigma z is 1. And then this 40 corresponds to some z here. I need to figure that out. It does make more sense, doesn't it? Because the other one doesn't make any sense. Again, we don't know what this is, but we're not done relating these two. Step 2 is not done until we figure out what the z is, because we have this labeled and this labeled. So we're going to need to label that z first. So in this case, step 2 is where the z-score formula is going to come in handy. If you recall, z equals x minus mu. I'm going to label this mu x divided by sigma x. And I'm labeling them with the subscripts to keep them distinguished from sigma z and mu z, right? Because this is mu z. So x is 40. Mu x is 30. And sigma x is 8.2 or 820. So that's going to be 10 divided by 8.2, which I don't know what that is. But I'm sure you guys will tell me. 10 divided by 8.2. That's going to be that's 100 divided by 82. 1.22. Somebody else back them up there. In any case, once we find that, we will be done with step 2. So I'll write that in as soon as you guys get there. Step 3. That's the end of step 2. Step 3 is to use z to get p or p to get z. In this case, I'm going to have a z, which you guys are about to tell me. Eli also says is 1.22. So it's going to be 1.22. And so 1.22 is what I'm going to use. I'm going to use that. Do you always have to draw the pictures? I get that question a lot. I'm not sure. Before I answer that question, can you tell me, why is there such a reluctance to draw the pictures? It's not that it just makes it a bit easier to visualize. I think it also manages to bring several parts of your brain together to cement it. But I'm curious, whence the resistance? I have a lot of students who are really reluctant to draw the pictures, and then like 6 months later, they still don't know how to do this stuff. And I'm like, well, if you'd started drawing the pictures at the beginning, maybe things would have worked out differently. And it's hard to know if like I'm a visual learner, but like I'm also an auditory learner. I don't know. I don't know that I buy all that because ink is expensive. Yes. Not a visual learner. So I don't know that I buy into the modes of learning research. It's not all that solid. What I will say is that the more modes of learning you apply, the better it is likely to be. And so pushing into areas of growth, I think can really help. You still know how to draw, but you like the numbers more. I would say if you can do it 6 different ways, successfully, you're more likely to get it right every way the one time. So the answer is no, you don't have to, but would I advise it? I mean, it's kind of like a doctor telling you that you should stop eating things that will kill you. Like you don't have to, you're not, it's not a moral obligation or maybe, I don't know, it's certainly not like illegal. But like how to be a good at things person, which is not a word, but you know what I mean? I don't know. I guess my belief is that people who draw the pictures for longer tend to do better than people who don't draw the pictures for longer. That said, I know people who have not drawn the pictures. Are they as good at it? Again, I don't think they are as good at it because it depends on who the person is, I guess. But yeah, I think you should be doing it both ways, right? You should be able to do it both ways. And in principle, with more time, I would like it if we could do it all of the ways where we're also doing it with a straight up math where we're saying the probability that x is greater than or equal to 40 is equal to the probability that a randomly drawn z is greater than or equal to 1.22. And then we have to figure out that value, which is 0.5 minus the probability that z falls between 0 and 1.22. I mean, these are all ways of depicting the same conceptual thing. So long story short, yes, exactly. That's back to hashtag salad with almonds, right? That's what this, it's all one big thought control. Okay, in any case, the short answer is actually, I recommend it highly, but I'm not going to make you. Oh, I see. There's a problem, which is that my head keeps going away because what I really want to do, oh, it is always on top. Okay, so if I put that, perfect. Okay, so to get z to p, now that we've wandered for a minute, you guys find it much easier to throw me off when we're online, I notice. We need to find 1.22. Fortunately, that's pretty easy to see here. We've got a z table, and if we go down to 1.2 and then go over to 0.02, hopefully you can see that that's 1.22, right? Because we got 1.2 here, and then 0.02, which add together to 1.22. So 1.22 gives me what value for p? That's what we need. And then while you guys are finding that specific value, I want to talk about the area. This is the real reason why you would want it, why I prefer the picture, Becca, just to kind of show you. No, it's fine. You're not in trouble, Becca, at all. I appreciate it. It's a good, I mean, it's important. It comes up a lot. So I'm glad that we addressed it. So thank you for that. The reason that the picture is useful is that a lot of times when people just work with the numbers, they forget which part of the table we're getting. Yeah, mostly it's me. I should have the restraint to just ignore you guys when I need to. But the part of the table, or the part of the curve that the table tells us about, is this part, which is to say, is the area between 0 and some particular value. And so if we just look up the value 1.22, it'll just give us a number, but that number is a little bit absent the context without knowing what its specific corresponding value is. Okay, Abu, I just see a period there. Were you trying to type something? I didn't see anything specific, and I think that's what I saw the other time too. So this yellow striped area is the part that we're getting from our Z table. And I see a few people there. Dalma's got it, 0.3888. That's where I was at. Okay. So when we go from 1.22 to 0.3888, it's important to remember that's this area here, which is not the area we care about. And drawing the picture helps us visualize that. It's hard to know. I mean, in some sense, math in this particular arena is sort of it relies heavily on the visual metaphor to embed in your brain the notion that the area under a curve is analogous to the probability of an outcome occurring. And so that the idea that we have an area under a curve, at least in my head, definitely draws to mind the physical representation of that area, the visual representation of that area, although it need not be. I mean, it's hard to imagine exactly how you could do like an auditory representation of an area under a curve, but it's not impossible. I've seen people do some weird stuff. So that's step 3, is Z to get P. Step 1 was draw this first picture. Step 2 was related to this. Step 3 was use the Z table to get 0.3888. And then the last step is to answer the question. And so if we recall, it's been a minute because we wandered a bit. If we recall, the question was asking, well, that's not you guys. The question was asking, here it is. What is the probability a company will have a stock price of at least $40? Well, the probability it'll have a stock price of at least $40, David's on it there, is going to be this area, which again is this area, which, yeah, we find that by taking this half, which is 0.5, and getting rid of the 0.3888. So we take 0.5 minus 0.3888, and we get to 111.0.1112. That's where we get it. Okay, so 0.1112 is the percentage, right? Because that is the size of this area, which is the size of this area, which is the visual metaphor for the question we were asking, which is, what is the probability a company will have a stock price of at least $40? It's 11.12%. Any questions on that one? The part B there, by the way, is just on the other side. The probability that a company will have a stock price no higher than $20. Well, Well, it turns out that puts it over here, right? $20, which is this area. I'm not going to go through the whole thing, but I want you to try to look at this and see that this area is going to be the same as this area, whether it's drawn the same or not, because this is $10, which is 1.22 standard deviations. Hey, that's my sister. This is $10, which will also be 1.22 standard deviations. Be quiet, Facebook. And that means that this area here is going to be the same as this area here, which means that this area here is going to be the same as this area here, which means that this area is going to be the same size as this area. So just looking at that, I can tell that those are going to be the same answer. Part A and part B are both going to have the same answer because they're both saying, what is the chance that, in the first case, what's the chance that you'd end up $10 higher than the mean? Yes, my sister's name is indeed Serenity. Our names got weirder. Jason to Lucas to Serenity as we got old, as my parents had more kids. And then I will be on this will be on YouTube later. That's right, Louisa. So feel free to bail if your injuries from your car accident are holding you back. And then the probability that it will be $10 higher is part A, and the probability that it'll be $10 lower is part B. $10 lower is part B. Cool. So part A and part B are the same. Part C is a little bit different, and this is like the one we did last class, which was what is the probability? I won't do the whole thing, but I'll just set up part 1 for you. You guys can do the rest. What is the chance that it'll be in the top 10%? We have the same mean, same standard deviation. Top 10%, that means this area is 0.1. And then we need to know what value puts us in the top 10%. That's step 1 done, right? So this area here is 0.1. And so step 2 is going to be related to the standard normal. We're going to have to look in the body of the table. But I want you to pay attention to the fact that this tail right here is 11%, and that puts us at $40. And so if it's going to be 10%, it's going to be smaller than that, which means I don't even need to know anything to know that it's going to be greater than $40. 40 something? I don't know what number it is, but just using the sniff test, if the upper tail is 11%, that puts us at $40. And so X here should be greater than $40. Again, I think that's one of the ways that the drawings can help, is to kind of wrap your head around that. Cool. So that's part C there. Okay, that should give you enough to work on the normal distribution problems. The ones up here, by the way, these are just asking you to, hey, Noah. Sure he is. Very nice of you to lie for Noah there, David. Just kidding, I believe you. But these ones are just asking you to use the table. So 613 and 615, they're not required, but they're excellent practice. So if you feel like the table is tricky, feel free to take a look at those to try to get an idea of how that can help you. All right, so that is the normal distribution. We will come back to the normal distribution and spend a fair bit of time on it because it turns out that things in the world are normally distributed. I'll show you that if we have some time at the end of class today. I'll show you a video of that. But first of all, or before that, I want to cover the last continuous distribution. And this will be the last of the distributions we learn for a while. So we've learned a bunch of them, but this is the last one, certainly the last one that'll show up on the exam. This one is called the exponential probability distribution. And the exponential probability distribution is related to Poisson. If you remember, Poisson was occurrences in an interval. Occurrences, I can never remember how to spell that. All right, that was X. In this case, X is the interval between occurrences. So I want to draw that distinction clearly in your mind. These two things are related, but let's say, for example, anything you should fix in this spreadsheet. Abina, I'll take a look at it later. let's say that these are occurrences that are happening. So let's say we have 0 minutes, actually, 0 minutes, 10 minutes, 20 minutes, 30 minutes as time goes forward, right? This is time. And then as time goes on, something happens here, and then something happens here, and then another one, and then another one here, and then nothing for a while, something here, something here, something here, something here, something here, something here. Poisson would be like, let's take a randomly selected 10 minutes, which is that distance roughly. X is the number of occurrences. In this case, that looks like there are 3 for Poisson, right? And that would tell us that. And then like we take another randomly selected 10 minutes, which looks like it's this amount. In this case, that would be 2, right? X equals 2. And that would be Poisson. For exponential probability distribution, what it would be is, let's take one occurrence. How long is it before the next occurrence? This amount of time, this is X. X is the length of time, right? And then let's pick another random occurrence. Let's say this one here. How long is it before the next random occurrence happens? And so that's what the exponential measures, right? So sometimes this is used for modeling survival. And by survival, we mean, it's sort of a technical term, meaning how long does, when one thing happens, how long does it take before it ends? So for example, you could use it to model the probability that a firework will last a particular amount of time before it stops working. You could use exponential probability to do that. But it's often used just to model durations in time between outcomes. So for example, let's talk about the example we dealt with before with the call center. Okay. So if they averaged, there's the call center. If they averaged 6 calls every 10 minutes, then for Poisson, that's what we would want, right? That would, then the average here was 6, right, in a 10-minute interval. And then we could use Poisson with a mu of 6 if what we cared about was the number of calls. But another way to think about this is to say that over 10 minutes, they average 6 calls. And at this point, we're talking about sort of when the call starts, right? So we're imagining that the call occurs. And then once that first call occurs, how long is it before the next one occurs? Well, that's saying that there's an average of 1.6 bar minutes between calls, between call starts. Okay? We want to model the probability of the length between any 2 calls. So we want to know how long it's going to be. Once we know a call has started, how long is it going to be before the next call? Is it going to be 1 minute? Is it going to be 2 minutes? Is it going to be 1.5 minutes? And hopefully you can see that this is a continuous distribution, right? So X now, X is the time until the next call. And that's continuous because it could be any number of seconds, so it could be a decimal. Well, it turns out that the exponential probability function lets us do that. And so there are actually 2 functions here that I want to talk about. The first one, so 2 functions. The first one shows us how to draw the curve. And that is called the probability density function. Hold on, let me take a look at what you just posted. Yeah, I know you're in there. Thanks, Abu. So the probability density function looks like this. F of x equals 1 over mu times e to the negative x divided by mu. So just like with Poisson, we need to know mu to be able to draw this. Okay. So that's what this curve is to show us how to draw the curve. Or that's what this, yeah, that's what this function is for, how to draw the curve. Let me move it down here so that I can draw it so we have some room. So let's draw this. I'm going to draw it in the general case, not the specific case here that we had. So this is f of x. This is x. That doesn't need to be in parentheses. What am I doing? Just x. Let's imagine that x is 0. Okay. Well, if x is 0, so what's f of 0? If x is 0, this is going to be 1 over mu times e to the negative 0 over mu, which is 1 over mu times e to the 0, which is 1 over mu. And so the beginning of this curve, the intercept of this curve, is always 1 over mu. Cool? But then what happens as x gets really large? Well, as x gets really large, we're essentially taking e and we're raising it to a larger and larger negative power, which means that this curve starts to go like this, starts to steadily decline, but then it asymptotes because it never becomes negative, right? And so that's what this curve looks like. Okay? You can kind of see if we were to, pardon me, if I want to calculate this for a bunch of different values here. Here. I can show an example of this. If we've got x, mu, let's give ourselves a mu. Let's just say mu is 3, just picking a random number for now. Just not. Thank you, Ray. Do 1 over mu. Thanks, Abu. And then e negative x divided by mu. Let's say we're at 0, and then 1 over mu equals 1 divided by this. And then negative x divided by mu is going to be negative this divided by this. And then e raised to this thing equals x raised to this. And then our f of x is just going to be 1 over mu times my e, just to show you how you would how this calculates out. Now, if I just add like 0.01 here every time, oh, that's supposed to be raised to the. Oh, I see what I did wrong. Sorry. Okay, now you can see what happens is that it starts to go down. If I change this to plus 0.1, it goes down faster and faster, so on and so forth. And you can see f of x starts to decline. And if I were to draw a scatter plot, you can really see it. So let's change this to 0.2 to make it a little bit more visible. So the scatter plot of this will show you the curve. So this is how you make curves in Excel, by the way, if you've never seen it before. Create a function like this, go to Insert, Scatter, Connected, and there you go. And so that's the curve. See? That's what the exponential curve looks like. If I change this to 0.3, it's much faster. And so that's the exponential curve. That's what it looks like. Which that's totally what I drew, right? You can totally tell that from what I drew. That looks the same as this thing. In any case, that's how we draw the curve. That's what that formula is for. So f of x equals 1 over mu times e to the negative x over mu. In practice, how do I want you to draw this? Mostly, I just want you to draw it like a curve like that and then label the intercept. If you label the intercept, that tells me you know what you're doing. Okay? So for our case, where we had, Noah doesn't get it. Okay. Well, the short version is what I'm doing here in Excel is just creating a column of X's and a column of Y's, right? So this is my column of X's, and then I'm doing some math to that to build up a column of Y's. And so these are my Y's. This column right here is my Y's. And so if I make this wider, you can see that I'm just choosing a bunch of X's, choosing a bunch of Y's so I can plot a drawing. Just like you would in algebra class when you're trying to plot a line, right? Where you do like y equals 2x squared minus 3x or whatever, and you try to plot a parabola. That's what I'm doing here. I'm just plotting that line. Mostly to prove to you that I'm not just making this up. This is actually what it's shaped like. But for the purposes of like drawing it on your homework and stuff, once you know mu, and so in this case, mu was 1.6 bar. What you need to draw is a curve that starts at somewhere in the intercept and then goes whoop and then asymptotes to 0, towards 0, and then label your axes. And then this value here is 1 over mu, which 1 over 1.6 is 0.6. It will always look exactly like this. That's a good question, right? The beautiful thing about doing this in Excel, and that's one more thing I like about Excel, you think they should give me some paid endorsements or something, but I can change mu here, and no matter what I change mu to, it just lengthens it. So this actually will eventually asymptote to mu no matter what value I have here. So 0.1, the one we're actually just looking at right now, 1.666, that's this curve, but it doesn't matter what the value of mu is here, except for the fact that it just takes longer. And so in order for us to see it here, we'd have to increase our increment. Actually, I could just show you the easiest way to do this is you can have something like an increment where this now, instead of adding 0.3, it adds whatever I put there. I can make this 0.5 or 1. As you can see, it's it takes a longer increment to get to the asymptotic part, but no matter what it is, it'll always work its way down there. Make sense? So exponential curves always just have this shape. And if you want to see in my notes what it looks like, you might see it in D2L. This is the curve that I made that I wrote in my notes. That looks like that. Cool. And that's what it will always look like. Cool. So that's what an exponential curve looks like. It's a steady decline, and then it slows down as it gets closer and closer to 0. All right. Okay. So this, but if you're drawing this on your homework or on an exam, and you want to draw an exponential curve, that's what I would expect to see here, right? 1 over 1.6 bar is 0.6. And then you just start there and go whoop like that. I'm like, okay, now you know what you're doing. Cool. I'm glad that makes sense. Okay, so that's the formula that tells you how to draw the curve. So let's say in this example, we want to know what is the chance that we're not going to get any calls, or what's the chance that we're going to get a call within the next minute. Okay. We want to know the likelihood that we're going to get a call in the next minute. Now we start to rely on the stuff we've already learned about probability, which is to say the area for a continuous distribution is equal to probability. So we draw our curve. Step 1, draw a picture, same as before. The curve starts here at 0.6 and then declines steadily. And we want to know what is the chance that we're going to get a call within the next minute. Well, that is this area here. Now, the tricky thing is that knowing how to draw the curve doesn't actually tell us anything about the areas underneath. For the normal distribution, if you remember, we needed a table to look on here. For the exponential distribution, we actually have a formula that tells us, and this is called, and actually it turns out that every curve, every distribution curve has a formula like this, but sometimes they're tricky, so we just use a table because calculating it would be hard. But it's called a cumulative distribution function, or a CDF. And the CDF for the exponential is not super tricky. The exponential CDF okay. The exponential CDF looks like this. The probability that x, some randomly drawn value. Hey, Noah, welcome on your own computer. I think you were smart to ditch that jerk. Oh, wait, he's still paying attention. Sorry. Never mind. I wouldn't have said nothing, David. All right. So the probability that x is less than or equal to some value. is equal to 1 minus e to the negative x sub 0 divided by mu. Shots fired. Is that what I learned from Ray last class? So what that tells us, this is a little bit new, not super new, but it's just saying x0 now is just like where you plug in. You plug in a specific value. So it's excellent dressing. You plug in a specific value. So we plug in a specific value there, and this will just calculate that. This basically is a formula that calculates this particular probability for us, right? So if we want to know, is there going to be a call in the next minute? What we need to do is plug in 1. What is the probability that of all the randomly selected values that we're going to choose one that's less than or equal to 1? Well, that's going to be 1 minus e to the negative 1 over mu, whatever that is, which in our case is 1 minus e to the negative, and we already calculated 1 over mu because that's the height of the curve right here, right? This is 1 over mu. So I don't need to plug it in, but I could. But that's going to be to the negative 0.6. Okay? So now I need you guys to help me out. What is e to the negative 0.6? You guys can find that for me, right? Once we find out what e to the negative 0.6 is, we can figure out what the probability is that we're going to get a call in the next minute. Because then we can just subtract that value. And again, what we're trying to find is the area here. That's telling us the area in that shaded region, whatever that is that you guys tell us. And it turns out that's what the CDF's. A CDF is always a function that tells you the area under a curve to the left of a value. 5488. I get a second on that? But that's what a CDF does. Cool, we have consensus, 5488. So we're doing 1, wait, is that 1 minus 0.5488? Let's double check it. If we put mu in as 1.666 e to the negative mu, oh wait, that's e to the negative 1 over mu. 0.5488 is that value right there. 5488. Okay. So 1 minus 0.5488. And that's going to give me 0.4512. And so that's the chance that I'm going to get a call within the next minute. It's 45.12%. Okay. Now, let's say, for example, we wanted to know what's the chance we're going to get 0 calls for the next 2 minutes. Okay. Well, 0 calls in the next 2 minutes just means that we're not going to observe an X that is 2 or less. Where's the 0.9975 from? I would check the math on that, Dalma. Are you using 0.6 here? No, that didn't do it. Not sure where that came from, Dalma. Okay, so if we want to know what is the chance, and I can write this question down. What is the chance of no calls in the next 2 minutes? It turns out there are actually 2 ways to answer this question. One way to answer this question would be to convert our mu to a Poisson and find f of 0 for the Poisson, right? That makes a lot of sense. Cool. So if we did a f of 0 with Poisson, that should get us the same exact answer because it's the same phenomenon. But another way to do that is to try to find the probability that x is greater than 2. Okay? Because that's saying we'll get no calls in the next 2 minutes if we draw that picture. Again, I have x and f of x here. 0.6 is my intercept, and then it slopes down. I'm putting 2 here, and I want to know what is the chance that whatever my value of x is, that the amount of time before the next call, I want it to be longer than 2 minutes if I'm going to have no calls in the next 2 minutes, right? And so I'm trying to find this area here. That's the probability that x is greater than 2. Now, the CDF doesn't tell me about upper tails. It only tells me about the lower section. And so I'm going to be able to use my formula to find this. And what am I going to have to do in order to find my actual value I care about? I'm going to let you guys ponder that while I start to figure out the size of this area, right? Because this I can use my CDF for. And then you guys tell me how I'm going to use this. Probability that x is less than or equal to 2 is equal to 1 minus e to the negative 2 divided by mu, which is 1 minus e to the negative 2 divided by 1.6 bar, which I don't know what that is exactly. I have to look it up or calculate it. So let's get a new, let me just get a calculator tab up here. So I need to know negative 2 divided by mu. That's going to be negative 2. Well, mu is 1. Negative 2 divided by mu. That's negative 1.2, just straight up even. I guess that makes sense. Yeah, because it's this thing here is, what is this? This is 5/3. I'm taking 6/3 divided by 5/3, which is 6/5. Yep, that's negative 1.2. Now e raised to the negative 2 divided by mu is going to be e raised to this number. That's 0.301194. So 1 minus 0.3012 is going to give me 0.6988. I think that's right. I'm waiting on you guys to tell me what to do with this number now. Okay, so that's this blue area, right? So I think I did that right. I think this thing here is 0.6988. Actually, I don't like putting probabilities below the axis, so let's do it up here. This thing is 0.6988. But I need to find the upper area, right? Because that's the probability that x will be lower than 2 or equal to 2. I want to know the probability that x is going to be larger than 2, because that means that I can run to the bathroom real quick and get back if I did, as long as I don't wash my hands. Yeah, that's right, Eli. Yep. So because these two are complements, right? The total area under the curve here. And you can kind of see how the intuition here is similar to in the normal distribution when we try to find a tail, where we're subtracting from 0.5. In this case, the total area is 1. And so we're, because it's total probability. And so we're going to take the probability that x is greater than 2 equals 1 minus the probability that x is less than or equal to 2, which is 1 minus 0.6988, which is actually, wow, it's a number we've seen already, 0.3012. And so that's the chance that I'm going to see. Well, there's about a 30% chance that there'll be no calls in the next 2 minutes. Okay, one other thing I want to show you with this type of problem that you might run into is intermediate values, right? So we've already looked at a few of these, but let's, now that we've got that we've got a few of the mechanics down, let's look at the probability that x falls between 1 and 2, meaning that there's going to be a call and there's going to be another call, and the distance between those is going to be between 60 seconds and 90 seconds, right? It's going to be between 1 and 2 minutes. Again, I want to draw my curve. The height of the intercept is 0.6, and then after that, it asymptotes down. And now I want to go to 1 here, and I want to go to 2 here, and I want to know how to find the area here. And I want you guys to help me with that. Okay. And so in this case, we're going to need to think strategically, right? We need to develop a strategy for how to try to find that area. Oh, I forgot my open parentheses here. The only tool I have at my disposal is a formula that helps me find when x is less than or equal to some specific value. Okay. No, Abu, I cannot. I mean, I can. I will not, put it that way. It's not. I'm not physically incapable. I'm just unwilling to do so. Yeah, that's right, Brandon. That's what we're looking for, right? So visually, again, I guess apologies to all the non-visual learners out there, but visually, we want to know the area under the curve in this area, which we can find, right? That's the probability that x is less than or equal to 2. And then you can find the area under the curve in this area, which is the probability that x is less than or equal to 1. And if we subtract those, that'll give us our value that we want, which that's our blue value, right? That's the probability that x falls between 1 and 2. Just out of curiosity, Abu, why do you want there to be more multiple choice? Those feel harder. They're more risky, right? There's no partial credit on multiple choice. All right, so let's find these. Probability that x is less than or equal to 2. We already calculated that. That is this number right here, 0.6988. And that is the size of this area. All the way up to the top of all the way up to the curve, so lest we forget. Yes, Aisha, absolutely. It'll be the same as last time. You can either bring yours or you can use mine. The probability that x is less than or equal to 1, and yours can be one page front and back. Probability x is less than or equal to 1. We found that right here. That's 4512. So scrolling back down, 0.4512. I did that kind of fast. Hopefully it's on your notes, but let me go back up and show you. 4512 was what we figured out here. So the probability that x is less than or equal to 1, 4512. So putting that down here, that tells us this area here, horizontal lines, I guess. And so hopefully this makes it visually visible. This area is 4512. This area is 0.6988. And then this blue area is the difference between those two areas, right? So if we subtract these, you get 6.742. So the chance that it'll be between 1 and 2 minutes is 0.2476. Shrink that and move it out of the way a little bit so we can kind of see it in Excel as well. I really don't need to keep showing you my meal plan. But if we look at the this curve here, what we're looking at here then, and you can kind of see it in scale here. If you imagine, let's see if I can insert shapes here. We're looking at this area here. Oops. From 0.6 down to here, over to 2, up to 2, and then back again all the way up here. And that's the first 6988. And then if we were to insert another one, where'd that go? There we go. We're subtracting this one trapezoid or near trapezoid to find out how much is left in this upper area. And it turns out the two combined make 69.88%. This big one's 45%, and this little one is 25% roughly. Cool. And so that's how we can use the exponential to find intermediate values. All right, so now we can find upper tails, lower tails, and then things in little segments in between or sections in between. Cool, so that's the exponential distribution. Let's do one practice problem from your problem set, and then I think we'll call it a day. Let's see, where's your problem set? Problem set 8, there we go. All right. Let's look at security screening at the airport. And in the news. The time required to pass through security screening at the airport can be annoying to travelers. The mean wait time during periods at Cincinnati/Northern Kentucky International Airport is 12.1 minutes. Assume the time to pass through security screening follows an exponential distribution. What is the probability that it will take less than 10 minutes to pass through security screening during a peak period? Okay, so let's see. We've got 12.1 is our average. So if we want to draw our picture, we're going to start here. One over 12.1 is going to be the height of this, which I don't know what that is, but we can figure it out easily enough. Again, with a meal generator, I don't need that. So mu is 12.1. 1 divided by mu, 0.0826. And so that is the height of this, 0.0826. All right. And then I want to know, what is the probability that it will take, just to double check again, what is the probability it will take less than 10 minutes? So let's go over here to 10, call this 10. What is this probability over here? Well, I have my cumulative distribution function. And if I recall what that says, it says that the probability that x is less than or equal to a specific value is equal to 1 minus e raised to that value, negative that value, divided by mu. And I'm pretty sure that mu was 12.1, and sure enough it was 12.1. Oh, hi, Emma. Thank you for letting me know. I'm glad you were able to make it. I'm sorry for that link was busted before. I was glad I was able to fix it so everybody could watch. Okay, so in order to calculate this, then I need to switch back here. I need to, the time I care about is 10. That's my x. And then we got negative x divided by mu. It's going to be negative 10 divided by 12.1. And then we've got e raised to the negative x divided by mu. That's 0.437. And now I've got 1 minus, copy this so I don't have to retype it. 1 minus this thing is going to be 1 minus this. 0.5624. Write it by hand just to keep it relatively clean. 1 minus e raised to the negative 0.826 equals 1 minus 0.4376, which is 0.5623. Or 24. 5624. Bad, bad, bad. Cool. So what is the chance that it will take less than 10 minutes to get through the line at Cincinnati Airport? It probably will take less than 10 minutes to get through. Sorry, my calendar popped up. It probably will. 56.24% chance, right? Hopefully that feels relatively straightforward, even though we just learned it, but practice will help. What else do we have there? Anything else worth learning, or any other practice problems worth learning there? I don't think so. I think that just about does it. Part D is a little more complicated. It asks us to figure out how much time it will take us. A clean example. Okay, cool. I hope that, yeah, that's right. It's always handy to have one after we're done teaching and learning to just kind of have a blank. The part B asks us more than 20 minutes. And so that's just trying to find this area here. We looked at kind of how to do that. Looked at kind of how to do that already. Part C asks us between 10 and 20 minutes. We learned how to do that already. And then part D asks us to think a little bit. If you get there at 8 a.m., you have to be at the gate within 30 minutes. It takes 12 minutes from the time you clear security until you reach your gate. What's the probability you'll miss your flight? Well, if it takes you half an hour or if your plane takes off in half an hour and you have to finish going through security 12 minutes before before the plane takes off, that means you have 18 minutes. And so then the question is, what is the chance that you'll miss your flight? What's the chance that it'll take more than 18 minutes to go through security? But again, it's just logic at that point, trying to think critically. And by just logic, I mean the actual hard part of all this stuff is being able to use your brain to try to think about the world we live in and how any of this stuff relates. It really does relate very directly, but it's not always obvious. And so sometimes you have to think about it. Cool. That's where the next exam is going to start or end, right? So that's the last thing that will be on the next exam. We are going to go from here, by the way, to talk about sampling a little bit, and to show you why the normal distribution is so valuable. I'm happy to field questions, by the way, as we go, but I wanted to show you a video of an example as to when the normal distribution comes in handy. While I have you here, which is the one that I shared. You may have already seen it. I posted it to D2L or to Slack a while ago. But if you didn't watch it, it's worth watching now. But I mentioned just a moment ago that the normal distribution, or that all this stuff is relevant to our life, to how the world works. And it really is. And it turns out that nature just kind of fits into open a new window into these probabilistic shapes. So here's a YouTube video. I don't know if you guys will be able to hear it. I don't want to hear it, because what's more interesting is what it looks like. And so that you can see, talked a little bit about, I don't know if I talked about Plinko at all. But if you build a big Plinko board like this, where you have lots of little pegs, and you drop balls down those little pegs, and you can see what happens when you drop just hundreds of these balls. That drawing there is a drawing of a normal distribution with a known mean and standard deviation. And just by random chance, the randomness, which is to say you don't know where any one ball is going to fall with certainty, but you can be pretty sure that the pattern that the set of balls will make will be roughly this pattern, right? And it will be no farther away from this pattern than a particular known amount away. It turns out that knowing that the uncertainty in the world has this particular shape has really strong implications for the probability of witnessing particular events. And so yeah, where we're going to go is how do we use the fact that this pattern shows up in nature to learn more about the likelihood of some things being true or being false, and also to come up with guesses about the population based on the data that we see. Noah, you had a question. You wanted to know if I would make a YouTube vid. That is what I just did. This YouTube video, what we just did, will be available on D2 or on D2L at this URL. Whatever you're watching now, if you bookmark the link that you're at now, you want to come back, you can watch this. You can pause it. You can mute it if what you want to do is just watch and you don't want to listen to me. Dom, are we back in the classroom Tuesday? At the beginning, I talked a little bit about that. To the best of my knowledge, where things stand now is they're supposed to be done with repairs on Sunday. So we should be back in the classroom Tuesday for the exam. If that changes, I will let y'all know what the new plan is. But for the time being, we're back in the classroom Tuesday with an exam in A1880. I don't actually know which bathroom exploded. Do you guys know where the bathroom explosion was? Was it on the food service side or was it on the other end of the building? For some reason, I was imagining the other end of the building, but since somebody got hurt in the food services section, it seems more likely that was the case. So I'm not sure. Tell me. Any other questions? If you guys are good, you can go. Thank you very much. It was the one by our classroom. Okay. That's pretty crazy. Yeah. I hope she's okay. Yeah. But yeah, I'm available to answer questions. I probably will not be on campus again this week because I kind of have to be at home in order to do this. Just because this is where I have my Wacom pad. By the way, if you want to see what the pad is that I'm writing on, it is a Wacom bamboo pen and tablet. And that's what I write on. I can't see what I'm writing on. I have to look at the screen, but that's what I'm using. So I have to be home to do this just because this is where I have my layout. So I'm probably not going to be on campus this week anymore. But I'm happy to web chat with you. Happy to talk on the phone with you. If anybody has any questions, let me know. I should be on campus next Monday. So if you can look to book time there if you need to, or try to stop by and see if I'm around, that could work. Questions. Any other questions? Well, I'll hang out for a few more minutes if people have questions, but thank you guys very much. And thank you for your flexibility. I'm really sorry that we didn't have access to the classroom. There's nothing I can do, but I wish I could. I feel bad that we don't have the resource. See you, Jason. You should, and hopefully you will soon. All right, if I don't see you, I'll see you Tuesday, okay? Good job, guys. Nice work. Don't forget to get your problem sets in by, I push the deadline back, right, by Saturday. So that's when they're due. Yeah, the lag, right? It's frustrating. The test is Tuesday, Noah. Tuesday, normal class time. Tuesday. See you, Ray. See you, Aisha. See you, Noah. And that's it. I'm out. Off to do other stuff to make the world a better place. See you all next week. Bye.